Hi, we are doing series of video lectures on digital communication. We have started module number 5. Today the topic of discussion is frequency hopping spread spectrum. In the last video we have discussed PN sequence. PN sequence are the code which are responsible for doing spread spectrum. So today we're going to study about frequency hopping spread spectrum. If we are using a digital modulation technique FSK, non-coherent FSK, so to get additional bandwidth we can use this technique. Okay, remember the kind of modulation that we do must be non-coherent FSK, frequency shift keying, then only you can use FHSS as spread spectrum technology. Alright, so what it is, okay, in this technology what is going to happen, instead of one carrier frequency, the carrier frequency will keep on changing during the course of transmission. The carrier frequency that we use for modulation, it is keep on changing. Okay, and in frequency shift keying what happens, basically frequency of the carrier changes, but here not only once, it will keep on changing. Okay, sometimes it is going to change fast, so it is called fast hopping. Sometimes it is going to change slow, so it will be called as slow hopping. So let us see what happens exactly. So in FH spread spectrum, the available channel bandwidth is subdivided into large number of non-overlapping frequency slots. So all the frequency, that means all the bandwidth and all the time. So bandwidth will be allocated, all the frequency that will be allocated, and all the time that is allocated, that makes a two-dimensional plane, will be divided into non-overlapping slots. Those slots are called independent frequency slots. Okay, so let me tell you, suppose this is the allocated time and this is the frequency allocated for transmission, and let us say that there are multiple users. So these users are given by these parallel lines. Okay, 1 2 3 4 5 6 7 users are using this channel. Okay, and this is the time allocated, and these at every time, okay, every some seconds, things will be going, or frequency will be changing from one frequency to another frequency. Not the message signal is going to change, it is the carrier frequency that will be changing, keep on changing. Okay, so those intervals are given by known as chip interval. TC means chip interval. Okay, now what happens in in any signaling interval, that is TB. Signaling interval means signal interval, the bit interval is TB. In any signaling interval, the transmission signal occupies one or more slots. So either it can these are the independent slots, these many independent slots are there, 7 cross 7. Okay, so out of that, what can happen, within one bit duration, either it can acquire multiple slots or one slot, depends. If it requires multiple slot, that means hopping is happening very fast rate. In that case it will be called fast hopping. If it acquires one or less than one, and then it is called as slow hopping rate. Okay, the selection of frequency slot, how this frequency will be changing, who decides in what way, in what manner, on what will be the pattern for frequency change. So that will be decided based on the PN sequence. Okay, so at the transmitter as well as at the receiver, you will have some PN sequence generator which will be generating some length of bits. PN sequence are nothing but binary bit sequences, but they are generated randomly. To know more about the PN sequence, you can refer previous video of the same module number 5. Okay, so remember three things I have mentioned here. First of all, overall this time and frequency two-dimensional plane will be divided into slots, and these slots will be chosen independently one by one based on the PN sequence generator. Okay, either this hopping can happen very faster rate, that means within one bit duration carrier signal will change multiple times, that will be called fast hopping. Or else if it is slow, that means TB is equal to TC or less than TC. Okay, TB is equal to TC or less than TC, and then in that case it is called slow hopping. So this is the way frequency will hop. It will hop like this. Okay, one frequency, then next frequency, then keep on changing. So you see, it is keep on changing like this, keep on hopping. Okay, so 7 times frequency has been changed. Now your bit duration, let us say your bit duration is given like this. Okay, so this is the bit duration. Within one symbol duration, that means TB, bit duration TB, how many times frequency, carrier frequency have changed? 1, 2, 3 and 4 times. 4 times it have changed. So within one duration, 4 times changing means the rate of hopping is very fast. So it comes under fast hopping spread spectrum. Alright, let us see the block diagram of FHSS. This is the block diagram here. The one which is represented in dotted line is called the transmitter section. So you see it is a simple digital communication system. What happens? There is a PN sequence generator. These PN sequence generators are binary bits. Depending upon the combination of binary bits, frequency synthesizer will synthesize or generate some frequency. This frequency will go and add up with the original carrier frequency. So every time this will generate some sequence. Based on this sequence, frequency will be generated, and this frequency will be mixed with the original carrier frequency. So suppose original carrier frequency was 1 megahertz and this was 1 kilohertz. They both will be mixed and will be 1.1 megahertz. Okay, if it is constructive. If it is destructive, 1 megahertz minus 1 kilohertz. Okay, so 999 kilohertz, like that it will become. So either it can up convert or down converted, that depends upon mixer. Okay, so PN sequence generate will sequence, based on that frequency will be generated or synthesized. That frequency will go and mix with the original carrier frequency. So overall a new frequency you will get, that is a changed carrier frequency. Now this can happen very fast or very slow depending upon the PN sequence. Okay, so let us see here. So the first thing is the modulation technique must be FSK, coherent FSK. The second thing is the resulting FSK signal is translated in frequency. Translated in frequency means the frequency will change. From original frequency it will translate to some other frequency because of this mixer. PN sequence will generate code, new frequency will be generated. This new frequency will be mixed with the original carrier frequency to get a fresh frequency, carrier frequency. Every time new PN sequence, a fresh frequency will be generated. Okay, like that the carrier frequency will keep on changing. Okay, now how many possible combinations you can have, how many carrier frequencies you can have? It depends upon, entirely depends upon PN sequence. So if PN sequence have m bits, okay, if it is generated from m bits, then you can have how many? 2 raised to m minus 1 possible carrier frequencies. Suppose you have a 4-bit PN sequence generator, have generated a PN sequence of 4-bit. Then you have 2 raised to 4 minus 1, 15 times frequency, 15 new frequencies will be generated. Okay. Now let us go to the block diagram again and see the dotted part is now receiver. In the receiver, the same process, except we have a time synchronizers which can sync the timing. So it is very important that it will be timely synced, so that whatever PN sequence that we have given, the same PN sequence will be available with the receiver to decode the signal. Okay. So pseudo random frequency translated into the transmitter is removed as a demodulator by mixing synthesizer output with the received signal. Okay. The resultant signal is then demodulated via FSK demodulator. Alright, a signal for maintaining synchronization in PN sequence generator with received signal. So with received signal, there must be some sort of synchronization mechanism which can provide proper synchronization. Okay. What are the types of frequency hopping spread spectrum? We have already discussed. It can be either fast hopping or slow hopping. Okay. Let us see the case here. Suppose this is, okay, let us say this is time and this is frequency. Okay, and these many users you have. Okay, like this, and these are the chip intervals. Okay, TC, 2 TC, 3 TC, 4 TC, like that. So within 1 bit duration, let us say within 1 bit duration, this is the bit duration. Let us say this is TB. Within 1 bit duration, frequency have changed, okay, 3 times. 1, 2, 3. So 3 times, okay. That means what I'm saying is you can generalize this if TB is equal to n times of TC. That is called fast hopping. Just now we have done an example of fast hopping. You can see TB was equal to 3 times of TC. That means within 1 bit duration, 3 times carrier frequency has been changed. So definitely it is, I can generalize that if TB is equal to n times of TC, then it is called fast hopping. Or I can say TB is 1 by RB, bit rate, in terms of bit rate. So n by RH. So since TC is equal to 1 by RH, RH is hopping rate, TC is chip interval. So RH is equal to n times of RB. So in frequency hopping, fast frequency hopping spectrum, this is very important. You can solve numericals with this. In fast frequency spectrum, the hopping rate is the integral multiple of bit rate. RB is the bit rate. Hopping rate is integer multiple of bit rate. This is called hopping rate. RH is hopping rate. Okay, hopping rate. And RB, you know, RB is bit rate. So hopping rate is n times of bit rate in fast hopping. Okay, fast FHSS. Then what is slow FHSS? Slow FS is very simple. It might require more than 1 bit duration to change one carrier frequency. Like this, let us see. So this is time, this is frequency, and these many users you have. So might be this is TC, 2 TC. Okay. Let us say this TC is equal to 2 or 3 times of TB. So this here is equal to twice of TB. So you can see it requires 2 bit duration to have one change in the carrier frequency. Okay. So it takes one frequency here, like let us say, then it takes another 2 TB to go for another frequency. So change is happening, change in carrier frequency is happening here rather slow. So change is happening here rather slow. What I mean to say is here TC is equal to n times of TB, or 1 by RH is equal to n by RB, or the bit rate is equal to n times of hopping rate. Okay, this is important. RB is equal to n times of RH. Okay. Same thing is written here. The frequency hopping rate denoted as RH may be either equal to or greater than, lower than, anything is possible from the normal symbol rate. If RH is equal to or lower than symbol rate, then slow hopping. But if RH is higher than the symbol rate, then it is called fast hopping. So remember 2 things I have told you. First condition here, fast hopping indicates TB is equal to NTC. Slow hopping is ulta. TC is equal to NTV. Okay. Now TB is equal to 1 by RB. RB is called bit rate. And TC is equal to 1 by RH. R is called hopping rate. Okay. So accordingly you can derive in terms of bit rate and hopping rate. All right.